Hi everyone. This lesson is going to be a quick example of how we solve a problem like this using exponential functions, or functions with variables in the exponents. So let's see what we have. A sample of carbon from an ancient midden has only 40% of the original amount of carbon-14 present. Carbon-14 is known to have decayed at the rate of 1.2% per century from the time the midden was used. How old is the midden? So let's get a little bit of an idea here. If we were to do a graph, time would be this axis and the unit is centuries. Now when time equals 0, we don't know how much carbon-14 is present. Let's call this amount N naught, N being the number of carbon-14 atoms. You could use any pronumeral you like, but the little subscripted 0 means it's the original amount. Now after 1 century has elapsed, we have lost 1.2%, so we're no longer there. We're somewhat down a little bit. We're not at 100% anymore. We're down by 1.2% compared to what we had. After 2 centuries, however much this was, we're down a little bit by there. How much are we down? We're down by 1.2%. Now please note that this drop here will be greater than this drop here, because although it's both they're both 1.2%, they're 1.2% of different amounts, and this gives me my idea. The amount present, and let's label. I might just move my little n naught slightly. Actually, let's just rewrite that. This axis is n, number of atoms, and that particular value there is n naught, the original amount. So this gives me an idea. This variable compared to this variable. So I know that I had some amount to begin with. Now, how much is a reduction of 1.2%? What is 100% of something minus 1.2% of that thing? Well, that would be 98.8%. So another way of saying a reduction of 1.2% is to say we still have 0.9, we multiply by 9.988. Yes. Now, if we were only 1 century later, we would have that to the power of 1. If we were 2 centuries later, we would have to have this to the power of 2. But we don't know how many centuries later we are. So if we are t centuries later, we will multiply this, raise this to the power of t. Altogether, that's going to calculate for me the number of atoms present. This is a variable. That's the capital N on the axis, and that represents the decreasing number of carbon-14s. T is a variable representing time in centuries. Now, we don't know how many we began with, do we? So let's go back to the question for a clue. A sample of carbon-14 from an ancient midden, so somewhere further down the track here, at some unknown time, we're told that this is 40% of the original amount. 40% of the original. So we don't know how much the original is in numbers, but we know this amount here is just a bit less than half of what we started with. Okay, I'll write that down. N equals 0.4 times n naught. Now I am going to write this instead of n. 0.4 by n naught should equal n naught 0.988 to the power of t. I can divide both sides by n naught. So they're gone. Now I have number 0.4, number 0.988, unknown value t. And as t is an exponent, the way to solve this is with a logarithm. So I will say the log of 0.4 to the base of 0.988 equals t. And this is a job for my calculator. Here I go. Remember the maths key. Base of 0.988 and the number is 0.4. 75.9, let's say, or we can go a bit more than that. T equals 75.9 sounds good. T equals 75.9 and the time was centuries. Well, that seems like if centuries we multiply by 100 years, it seems like just a bit less than 7,600 years would be the age of this thing. Now, we can do this on our calculator as well, on our graphing mode. Not that we need to, this is just for fun. We don't have a number for n naught, do we? So let's just give it the number 100. Let's pretend there are 100 carbon-14 atoms when we start. Maybe there's a lot more than that. And I will go to the power of x. So my graph, when I draw this, I can't see anything. I'll check the view window. Now, what did we find out? We thought that we were going to have to go across to about 76. Let's go across to 100 and we'll jump up in steps of 10. Well, y maximum, I said there was 100 atoms to start with, and let's jump that one up in steps of 10 as well. Now we should see something. Look at that, there we go. So this is my 100 atoms. This is 1 century later. If I press the trace function here, and I just press 10, so 10 centuries later, I meant to do 1 century, didn't I? Just 1 century later, just a teeny little step. Look at that, we're at 99.8 atoms, because that's the 1.2% reduction. If we were to go to 2 centuries later, now this is 1.2% reduction of the 0.988 that we had a moment ago. Now, let's see if we can keep on going until we get down to, we're looking for this to be 40% of the original, or 40 atoms. Keep on running down there, getting close, getting very close. Oh, that's about as best as I think I can do. And what have we got? 75.9. Very close to the answer we had. We could also do this with gsolve. And on gsolve, we can ask for, now we want to give it a y value and it's going to calculate the x value for us. So we want a y value of 40 and it calculates exactly the answer that we had from our calculator. Isn't that nice, the way these calculators can help us out like that? So that is a nice little example there of a exponential equation involved, went too far, involved in a lovely problem solving scenario. And this is exactly the sort of thing that archaeologists look at when they find an ancient relic and they want to use carbon-14 dating to figure out how old it is. And that's exactly the mathematics they would use. I hope that helped. Thanks for watching.